A single photon can cross the cosmos untouched for billions of years. Light is the universe's first and fastest messenger, and its speed is the ultimate key to unlocking everything from the birth of stars to the nature of time itself. By the end of this journey, you will see how a simple constant reshaped our entire reality. We will uncover why a tiny anomaly in Jupiter's moons cracked this cosmic code, and how ghostly particles now challenge everything we thought we knew. What part of this endless race to understand the universe sparks your deepest curiosity? The idea that light streamed from our own eyes is a strange and beautiful thought. Long ago, the Greek philosopher Empedocles truly believed this was how vision worked. He imagined that we reached out with beams of light from our eyes to touch the world, illuminating objects so we could see them. This was humanity's first real guess at the nature of light, a profound question asked in an age of pure observation. It was a deeply human-centric view of the cosmos, placing us as the active source of illumination. But then came other thinkers like Aristotle, who challenged this idea. He proposed that light was a state of a transparent medium, something in the air itself. For centuries, these philosophical debates swirled without a clear path to an answer. The real turning point arrived with the work of an Islamic scholar named Alhazen in the 11th century. He moved the conversation from pure thought to tangible experiment. Alhazen designed simple but brilliant tests with lenses and mirrors, carefully studying reflection and refraction. He demonstrated that light must travel in straight lines into our eyes, not out from them. This was a monumental shift. It marked the moment we began to interrogate light itself, to ask it questions through careful observation. Was light made of tiny particles, a stream of corpuscles as some suggested? Or was it a wave, like a ripple moving across a pond? And perhaps the most baffling question of all, a question that seemed almost unanswerable at the time, did it even have a speed? Could its travel be measured, or was it instantaneous, arriving everywhere at once? These early minds, armed with little more than curiosity and keen intellect, laid the entire foundation for our modern understanding. They ignited a race to decode the universe's fastest messenger, a race that was about to accelerate in ways they could never have dreamed. The cosmic clock, it seemed, was running late. While observing Jupiter's moon Io from the Paris Observatory in the 1670s, the Danish astronomer Ole Rømer noticed something deeply puzzling. The tiny moon would dip into Jupiter's shadow at predictable intervals, a celestial metronome marking time across the solar system. Yet as Earth moved in its wider orbit, farther from Jupiter, these eclipses consistently fell behind schedule. When Earth swung closer again, the clock miraculously sped up to catch up. This was not a quirk of Io's orbit. Rømer made a breathtaking intellectual leap. The delay was not in the event itself, but in the news of the event reaching us. Light was not instantaneous. It was a traveler, and it took time to cross the vast emptiness of space. Rømer's calculation was a stroke of genius. He estimated that light took about 22 minutes to cross the diameter of Earth's orbit. From this, he produced the first finite speed for light. His number was not perfectly accurate, but its impact was immeasurable. For the first time in human history, an abstract philosophical debate was settled with a hard number. Light was no longer just a mystery of perception or a divine emanation. It was a physical thing that obeyed laws and had a speed that could, in principle, be measured. This single idea transformed our entire cosmic perspective. We were no longer just observers of a static sky. We were participants in a dynamic universe, receiving news from distant worlds that was always inevitably old. The stars were not just points of light, they were beacons, and their messages were delayed. Rømer had given us the first true measure of the void, proving that even the fastest thing in the universe cannot outrun time itself. The race was on to pin down that number with absolute precision, and the next great leap would bring the question down to Earth. Rømer had proven light had a speed, but its true value remained a number sketched from celestial motions. To tame this cosmic constant, we had to bring it down to Earth. The 19th century saw this quest move from the observatory to the laboratory, transforming it into a problem of breathtaking mechanical ingenuity. In Paris, Hippolyte Fizeau conceived a brilliantly simple apparatus. He aimed a beam of light through the gaps of a rapidly spinning toothed wheel, sent it racing to a mirror over 5 miles away, and watched for its return. If the wheel spun at just the right speed, the returning light pulse would find its path blocked by a metal tooth. By knowing the wheel's rotation speed and the distance traveled, Fizeau could calculate light's velocity. His result was stunningly close to the modern value, all derived from the rhythmic click of cogs intercepting a beam of light. Then came Léon Foucault, who refined the method with a dazzling twist. He replaced the cogwheel with a rapidly rotating mirror. A beam of light would strike this spinning mirror and be deflected to a stationary one. In the tiny fraction of a second it took the light to make its round trip, the spinning mirror had turned ever so slightly, deflecting the returning beam to a new point. By measuring this minuscule shift, Foucault could calculate the speed with even greater precision. These were not abstract calculations, they were physical, tangible experiments. You could hear the whir of the machinery and see the spot of light jump. They took a cosmic mystery and made it a demonstrable fact of gears, light, and mirrors. This terrestrial triumph solidified the speed of light as a fundamental constant of nature, a number now firmly anchored not just in the heavens, but in the very world around us. The stage was set for a quiet patent clerk to ask a deceptively simple question, one that would shatter our understanding of this constant forever. James Clerk Maxwell's equations were a symphony written in the language of mathematics. He wasn't just tinkering with light in a lab, he was peering into the fundamental fabric of reality, discovering that the seemingly separate forces of electricity and magnetism were two faces of a single, unified phenomenon. His math described how a changing electric field could create a magnetic field, and how a changing magnetic field could, in turn, generate an electric one. This self-sustaining dance could propagate through space as a wave, and when Maxwell calculated the speed of this theoretical electromagnetic wave, the number was unmistakable. It was the speed of light. In that breathtaking moment, light was no longer just a thing we could see or measure. It was revealed as a ripple in the electromagnetic field, one specific note in a vast cosmic spectrum. The brilliant red of a sunset, the invisible warmth from a fire, the radio signals carrying voices across continents, and the X-rays that see through flesh and bone, they are all exactly the same thing, simply vibrating at different frequencies. This was the first deep reason why light had the speed it did. That number wasn't an arbitrary travel limit. It was a fundamental property of the universe itself, a constant woven directly into the laws governing space, time, and energy. Maxwell had handed humanity a key, a mathematical proof that light's speed was a cornerstone of reality. Yet this profound insight also created a puzzle. Waves need a medium to travel through, like sound needs air. So what was the medium for light, this wave crossing the emptiness of space? Physicists invented the concept of the luminiferous ether, an invisible, frictionless substance that supposedly filled the cosmos. But this elegant idea was about to collide with a revolution, one sparked by a quiet patent clerk who would ask what happens when you try to catch a beam of light. Albert Einstein looked at Maxwell's beautiful equations and saw a paradox waiting to be unraveled. If light was a wave in a universal field, then its speed should be relative to the motion of this mysterious ether. Yet every attempt to detect this ether, to measure our motion through it, had failed spectacularly. Einstein made the courageous choice to trust the math over the intuition. He proposed that the speed of light in a vacuum is not just a constant, but the constant. It is exactly the same for every observer, whether you are standing still, racing towards the source of the light, or fleeing from it at tremendous speed. This single, deceptively simple postulate became the foundation of his special theory of relativity, and it shattered our classical worldview. The consequences were as profound as they were strange. If the speed of light is truly immutable, then something else in the universe must be flexible to compensate. That something was space and time themselves. Imagine two observers, one on a speeding rocket ship and one stationary. Both measure the speed of a single beam of light and get the exact same number. For this to be possible, time for the astronaut on the rocket must slow down compared to the stationary observer. This is time dilation, a real and measurable effect. Similarly, the length of the rocket itself would contract along its direction of motion from the stationary observer's perspective. These are not optical illusions. They are fundamental properties of a universe where light speed is the ultimate, unbreakable rule. This cosmic speed limit, denoted by the letter c, imposes a profound restriction. Nothing with mass can ever reach it. As an object accelerates, its mass effectively increases, requiring more and more energy to go even faster. To actually achieve the speed of light would require an infinite amount of energy, an obvious impossibility. So light speed is not just a speed, it is the boundary of what is physically possible for matter and energy. It is the cosmic regulator that preserves cause and effect, ensuring that a signal cannot arrive before it is sent. Einstein's revelation forever intertwined the fabric of spacetime with the behavior of light, forcing us to accept that the universe is far stranger and more wonderful than we ever suspected. But if nothing can travel faster than light, how do we explain the ghostly neutrinos that seem to mock this very law? Every photon that reaches our telescopes is a cosmic telegram, stamped with the time and place of its origin. When we catch the light from a distant star, we are not just seeing a point of brilliance, we are holding a physical sample of that star, delivered across space and time. By sifting this light through a prism, we can spread it out into a spectrum, a unique barcode of color. Dark lines slicing across this rainbow reveal the specific chemical elements present in the star's outer layers, like a cosmic fingerprint. The subtle reddening or bluing of this entire spectrum, a Doppler shift, tells us whether the star is racing toward us or fleeing away. We can even measure its surface temperature simply by its dominant color. But light's messages go far beyond individual stars. The entire cosmos is filled with a faint, uniform glow of microwave radiation. This is the cosmic microwave background, the cooled and stretched afterglow of the universe's fiery birth in the Big Bang. It is the oldest light we can observe, a baby picture of the cosmos when it was just a hot, dense soup of particles. Then there are the cataclysmic explosions of dying stars, supernova. By studying the light from these incredibly bright events in galaxies far, far away, astronomers made a shocking discovery. The universe is not just expanding, it is accelerating in its expansion, pushed apart by a mysterious force we call dark energy. We only know this because the light from those ancient supernovae was fainter than it should have been, its journey stretched by the growing emptiness of space. So light is our ultimate data stream. It allows us to perform cosmic archaeology, reconstructing the history and evolution of everything we see from these ancient, luminous messages. But what happens when the universe sends a message that is not written in light at all? But light is not the universe's only courier. For decades, we believed it was the ultimate information carrier, the fastest possible messenger. Then we met the neutrino. These are the true phantoms of the cosmos, particles so elusive they barely exist in our reality. They have almost no mass and carry no electric charge, which means they sail through solid lead as if it were empty space. Right now, as you listen, trillions of them are streaming through your body every second, leaving not a single trace of their passage. Their ghostly nature once led to a stunning, controversial claim. In 2011, an experiment called Opera detected neutrinos that appeared to arrive from their source 60 nanoseconds faster than light would have. The scientific world held its breath. Had we finally found something that broke the cosmic speed limit? After months of intense scrutiny, the answer was a sobering no. A faulty fiber optic cable connection was to blame, yet that fleeting moment of possibility highlighted how seriously we take this fundamental rule and how these particles push our instruments and our understanding to the absolute edge. So why do we chase these phantoms? Because when a star dies in a cataclysmic supernova, its core collapses. The resulting flash of light is trapped, battling through the star's dense outer layers for hours before it finally bursts free into space. But the neutrinos, indifferent to matter, escape the collapsing core almost instantly. For a supernova in a neighboring galaxy, a surge of these ghostly particles would wash over our detectors hours before the first glint of visible light painted the night sky. They are a different kind of informant, carrying news directly from the heart of the explosion that light cannot immediately bring. This forces us to broaden our very definition of a cosmic messenger. The race is no longer just about catching light. It is about building colossal, ultra-sensitive traps deep underground to catch the whispers of these ghosts, piecing together a fuller story of the universe, one elusive signal at a time. The ghostly neutrino, for all its mystery, still carries a tiny packet of energy from a distant cataclysm. But what if the universe itself could ring like a bell? In 2015, a century after Einstein predicted them, scientists finally detected the first gravitational waves. These are not waves of light or particles. They are literal ripples in the fabric of spacetime itself, stretching and squeezing the very dimensions of reality as they pass. Imagine the cosmos as a still pond. When a truly massive event occurs, like two black holes colliding in a final, violent dance, it is like dropping a mountain into that pond. The impact sends shudders through the water, waves that travel outward in all directions. Gravitational waves are those cosmic shudders. They are the universe's fastest messengers in the purest sense, traveling at the absolute speed of light, but they are fundamentally different from anything we have discussed. Light from radio waves to gamma rays is an electromagnetic disturbance. It can be blocked by a cloud of dust, absorbed by a gas, or reflected by a mirror. Gravitational waves do not interact with matter at all. They pass through planets, stars, and you completely unimpeded. They do not bring us light or heat. They bring us a distortion of space itself. The first detection was so tiny, it changed the length of a 4-kilometer laser beam by a distance 10,000 times smaller than a proton. This monumental achievement opened a completely new window on the cosmos. For the first time, we were not just seeing the universe, we were listening to it. Every merger of dense, dark objects like neutron stars or black holes creates a unique chirp, a rising frequency that our instruments can translate into sound. This gives us a clean, direct signal from the most violent events, one that is not obscured by cosmic gas and dust. From that single signal, we can extract the masses of the objects that collided, their spins, and profound truths about the nature of gravity itself. With this new sense, we are tuning into the symphony of space-time, hearing the dark, violent corners of the cosmos that were forever silent to us before. Our planet has become a listening post, a grand collection of instruments all aimed at the same cosmic light stream. To truly decode the messages carried by light, we have built an armada of sophisticated observatories, each a specialized eye on the sky. Orbiting high above the distorting blanket of our atmosphere, the Hubble Space Telescope became a household name by delivering breathtaking visible light portraits of stellar nurseries and distant galaxies. But visible light is just one channel in a vast cosmic broadcast. The Chandra X-ray Observatory tunes into a far more violent station, seeing the searing, high-energy glow from matter spiraling into black holes and the superheated remnants of exploded stars. Then there is the James Webb Space Telescope, an infrared marvel designed to look back in time. By detecting the stretched, reddened light from the universe's infancy, it peers through cosmic dust to see the first galaxies flickering to life. Back on the ground, colossal instruments like the Very Large Telescope in Chile and the Keck Observatory in Hawaii use a brilliant trick called adaptive optics. They fire laser guide stars into the upper atmosphere, measuring the turbulence in real time, and then flexing their mirrors thousands of times a second to cancel out the twinkling of the stars. This turns the atmospheric blur into a crystal-clear view. Think of it like tuning a radio dial. Hubble listens to one favorite station, Chandra to a heavy metal channel of pure energy, and Webb to a deep, ancient frequency. They are not competing, they are collaborating, forming a collective sensorium for our species. Together, these technological marvels capture the universe in a full symphony of light, from the gentle infrared warmth of a planet-forming disk to the furious, fleeting flash of a gamma-ray burst. They are the indispensable tools in our race, the means by which we gather every precious photon to read the story of everything. Even as Einstein cemented light's speed as the ultimate constant, his own work helped reveal a deeper, stranger layer to reality. The quantum world operates by a different set of rules, a realm where certainty dissolves into probability. Here, we find a phenomenon that Einstein himself could not accept, famously dismissing it as spooky action at a distance. This is quantum entanglement. Imagine a single particle decays, giving birth to two photons that fly apart in opposite directions, perhaps across a room, perhaps across the galaxy. According to quantum theory, these twin photons are linked in an intimate dance. Their properties, like their polarization, are not defined until the very moment one of them is measured. The act of observing the first photon instantly forces its distant twin into a corresponding state. This connection appears to be instantaneous, seemingly leaping across any distance without any travel time. It feels like a violation of the cosmic speed limit, a faster-than-light whisper between particles. But here is the crucial distinction that preserves Einstein's law. No actual information, no message that you can control or encode is being sent between them. You cannot use this link to send a signal faster than light. When you measure your photon, the result is completely random. You only know what state its partner is in, but you have no way of influencing that outcome to communicate. It is like two people each taking one glove from a perfectly matched pair. The moment one person looks and sees they have a left-handed glove, they know instantly, with certainty, that their partner holds the right. Yet they did not send a message. The information was inherent in the shared origin of the gloves. Entanglement reveals a profound interconnectedness in the universe, a hidden unity that challenges our most basic assumptions about space and separateness. This is not just a philosophical curiosity. Our understanding of entangled photons is the very bedrock of revolutionary technologies. Quantum computers use these delicate states to perform calculations that would take conventional computers millennia. Quantum communication networks use entangled pairs to create theoretically unbreakable encryption, where any attempt to eavesdrop immediately disrupts the fragile link and reveals the intrusion. So light, in its most bizarre quantum form, is not just a messenger carrying news from stars. Its entangled photons are becoming the fundamental building blocks for a new kind of technology, proving that the universe's fastest messenger is also its most mysterious architect. The cosmic speed limit is not a suggestion. It is a law etched into the fabric of reality, a barrier that makes the dream of reaching the stars in a human lifetime seem like a fantasy. Yet the human imagination refuses to be caged. Science fiction has long offered tantalizing escapes from this rule, concepts like warp drives and wormholes that bend the very canvas of the universe to their will. Remarkably, these ideas are not pure fantasy. Theoretical physicists like Miguel Alcubierre have shown that general relativity, the very theory that established light's speed as the ultimate constant, might also contain the blueprints for circumventing it. An Alcubierre warp drive would not propel a ship through space faster than light. Instead, it would manipulate spacetime itself, contracting the fabric of the universe in front of the vessel and expanding it behind. The ship would rest inside a stable bubble of flat spacetime, a passenger on a wave of distorted geometry, effectively riding a shortcut while never locally breaking the speed limit. Think of it like a moving walkway at an airport. You are not running, but the ground itself is moving beneath your feet, carrying you forward at a speed the walkway dictates. Similarly, a warp drive would let the universe do the moving for you. Then there are wormholes, theoretical tunnels through the folded layers of spacetime. If our universe is a vast sheet of paper, a wormhole would be a pencil hole connecting two distant points with a near-instantaneous bridge. You would not travel the long way around, you would simply step through the cosmic shortcut. But there is a profound catch. Both of these incredible concepts demand a substance that may not exist, exotic matter. This is not just rare or unknown matter, but matter with truly bizarre properties, specifically negative energy density. Think of it as a kind of gravitational antigravity, something that could push spacetime apart rather than pulling it together. This exotic matter would be needed to stabilize the throat of a wormhole, preventing it from snapping shut the instant it formed, or to sustain the warp bubble around a ship. We have no proof such a substance is real, and the energy requirements are staggering, beyond anything our civilization could muster. So why do we even entertain these mind-bending ideas? Because they represent the ultimate endgame in our race to decode the universe's fastest messenger. We are no longer just trying to understand the laws of physics. We are asking if we can use the deepest, most subtle principles of those laws to engineer reality itself. This research, while speculative, keeps the most profound of human dreams alive. It proves that our quest is not just to listen to the cosmos, but to one day perhaps answer its call in person. Deep within the data streams from two lonely spacecraft, a ghost was hiding. The Pioneer probes, having completed their grand tours of the outer planets, were now speeding silently into the abyss. Yet as scientists tracked their paths, a faint, persistent whisper of a signal emerged. Both Pioneer 10 and 11 were experiencing a tiny, unexplained deceleration, an almost imperceptible tug back towards the sun. This was the Pioneer Anomaly, and for years it was a tantalizing glitch in the cosmic code. Could it be a sign of something profound? perhaps a flaw in our understanding of gravity itself, or evidence of some unseen, diffuse dark matter halo tugging at the spacecraft. The possibility of new physics hung in the air, a revolutionary secret waiting to be decoded from the trajectory of these human-made messengers. The answer, however, was far more ordinary, yet in its own way just as brilliant. A team of researchers embarked on a monumental detective hunt, digging through decades-old engineering documents and telemetry data. They realized the anomaly could be explained not by mysterious forces, but by simple heat. The spacecraft were powered by radioactive plutonium, and that decay generated a steady, faint warmth. This heat radiating from the probe's electronics panels was acting like a tiny, gentle photon thruster. Each photon carried a minuscule amount of momentum away from the craft, and over years and billions of miles, this constant, gentle push was enough to create the observed deceleration. The case was closed not with a bang, but with a thermal model. This episode stands as a monument to scientific humility. It reminds us that the universe is a master of illusion, and our instruments are imperfect extensions of our senses. Before we can hear the universe's true whispers, we must first learn to silence the sound of our own footsteps. Every mysterious signal is a puzzle, and the most elegant solution is often the one that requires us to look not out at the stars, but closely, carefully at our own machinery. Two of our most trusted cosmic measuring tapes are giving us different answers. This is the Hubble Tension, a quiet but profound conflict at the very heart of modern cosmology. On one side, we have the cosmic distance ladder, a meticulous step-by-step method built on the rhythmic pulses of Cepheid variable stars. These stars brighten and dim with a perfect regularity that reveals their true luminosity, allowing us to gauge distances to nearby galaxies with remarkable precision. By watching how fast these galaxies are receding from us, we can calculate the universe's current expansion rate, a number known as the Hubble constant. It is a measurement taken from the universe as it is today. On the other side, we have the oldest light we can see, the cosmic microwave background. This fossilized glow from the infant universe holds a snapshot of its early conditions. By studying the subtle patterns in this light, we can use our theory of the Big Bang to predict what the expansion rate should be today. The problem is stark. The number from the ancient light does not match the number from our modern observations. It is as if you calculated how fast a tree should have grown based on its seedling rings, only to find the fully grown tree is significantly taller than your prediction. This is not a small rounding error. It is a persistent discrepancy that has survived years of increasingly precise measurements. Could it be that our reading of the primordial light is missing a crucial piece of physics? Perhaps dark energy, the mysterious force accelerating the cosmos, is not constant but has evolved over time, changing its strength in ways we never anticipated. Or maybe our understanding of the universe's first moments is incomplete, and we need entirely new particles or forces to explain the data. This tension is more than a scholarly debate. It is a direct challenge, forcing us to ask a deeply unsettling question. Are we simply misinterpreting the messages from our cosmic messengers, or is the universe, in its quiet expansion, trying to tell us something entirely new about the fundamental laws of reality? The resolution of this puzzle is the primary goal for the next generation of telescopes, instruments that will peer deeper and measure more finely than ever before. They are not just looking for an answer, they are listening for a correction to our entire story of the cosmos. Light reveals a universe it cannot illuminate. For all its power, our fastest messenger has shown us the profound limits of our own vision, exposing a cosmos dominated by something we cannot see. This is the mystery of dark matter, the invisible scaffolding that holds the universe together. Its story begins not with a direct observation, but with a ghostly gravitational pull. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies. He noticed that these galaxies were moving so rapidly that the cluster's visible mass, all the stars and glowing gas we could detect, was far too little to provide enough gravity to hold them together. The cluster should have flown apart long ago. He concluded that there must be some unseen mass, which he called Dunkel Materie, or dark matter, providing the missing gravitational glue. Decades later, Vera Rubin provided even more compelling evidence by charting the rotation of individual spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, far from the bright central bulge, should orbit much more slowly than those near the center. Yet Rubin's meticulous work showed something startling. Stars at the galaxy's edge race around just as fast as those near the core. The only explanation is that each galaxy is embedded within a massive, invisible halo of matter, a vast sphere of dark stuff whose gravity whips the outer stars to incredible speeds. This unseen presence is not a small component. For every pinprick of light from a star, there is roughly 5 times more dark matter holding it in place. It is the universe's dominant architectural material, the framework upon which galaxies are built. But what is it? We know it is not made of the atoms that form you, me, or the stars. It does not interact with light at all. A galaxy-sized cloud of dark matter would be perfectly transparent. You could fly right through it and see the stars on the other side, feeling only its immense gravitational tug. The leading theory suggests it is a sea of as yet undiscovered particles, perhaps something like a WIMP, a weakly interacting massive particle that barely notices normal matter exists. Another, more radical idea proposes that we have not misunderstood the matter, but the force itself. Could our theory of gravity, Einstein's magnificent general relativity, require modification on the vast scales of galaxies? This idea, known as modified Newtonian dynamics or MUND, suggests that gravity behaves differently when it becomes exceptionally weak, creating the illusion of extra mass. The quest to solve this mystery has driven us to build extraordinary detectors deep underground, shielded from cosmic rays, hoping to catch the faintest bump of a dark matter particle. Other experiments aim to create them in powerful particle colliders. We are hunting for a ghost, using the subtle warp it creates in the fabric of spacetime as our only guide. This is the ultimate cosmic detective story, a case built entirely on circumstantial evidence, where the primary suspect remains forever in the shadows. Dark matter sculpts the cosmos, but dark energy is the force tearing it apart. For decades, we assumed the universe's expansion was a cosmic sigh, destined to slow under the relentless pull of gravity. Then, in the late 1990s, 2 independent teams of astronomers pointed their telescopes at a specific type of stellar explosion, a supernova that acts as a perfect cosmic mile marker. They were hunting for the deceleration rate, the precise amount by which gravity was putting the brakes on everything. What they found instead was a profound shock. The light from these incredibly distant supernovae was fainter than it should have been. This dimness could mean only one thing. Those stellar explosions were much, much farther away than our existing models predicted. The universe was not slowing down at all. It was accelerating, flying apart faster and faster with every passing moment. This was like tossing a ball into the air and watching it not only fail to fall back down, but shoot away into the sky at an ever-increasing speed. The discovery was so bizarre and counterintuitive that it earned the teams the Nobel Prize. It forced us to confront a staggering new reality. There must be something working against gravity, a mysterious repulsive force that we cannot see or directly detect. We call this force dark energy, and it is not a minor player. Current measurements suggest it makes up about 68% of the entire cosmos. Think about that for a moment. Nearly 7/10 of everything that exists is this unknown, expansive energy. Its nature is perhaps the greatest puzzle in all of modern science. So what could it possibly be? The leading idea is that dark energy is a cosmological constant, an inherent property of the vacuum of space itself. Empty space is not truly empty. According to quantum physics, it is a seething foam of virtual particles popping in and out of existence. This activity could endow every cubic centimeter of nothingness with a tiny, constant energy that pushes outward. This was an idea Einstein himself once proposed and then discarded. Another possibility is even stranger. Dark energy might not be constant at all, but a dynamic field that changes in strength over time, a sort of cosmic weather that is currently driving a rapid expansion. The ultimate fate of the universe hinges on which of these ideas is correct. Will this acceleration continue forever, leading to a cold, dark, and isolated end? Or could the strength of dark energy change, potentially even reversing one day? The light from those ancient supernovae was the messenger that delivered this stunning news, forcing a radical rewrite of our cosmic story. Now, the race is on to decode its next message, using the most powerful telescopes ever built to measure the expansion history of the universe with exquisite precision, hoping to read the subtle signature of this phantom force in the fading light of the stars. A black hole is a place where the universe erases its own messages. It is the final, absolute prison for light itself. Imagine the ultimate cosmic censorship, a gravitational force so overwhelming that not even the fastest thing in existence can break free. The boundary of this prison is called the event horizon, a spherical shell of perfect darkness marking the point of no return. Cross this invisible threshold, and every possible path leads inward toward the crushing singularity at the center. From our perspective outside, any light or matter that crosses the horizon appears to freeze in time, its image stretched and red shifted into oblivion before it simply vanishes. This is where our understanding of reality fractures, leading to one of the most profound puzzles in all of science, Stephen Hawking's information paradox. Hawking made the startling discovery that black holes are not entirely black. Due to weird quantum effects at the very edge of the event horizon, they can slowly leak a faint, random glow of thermal energy, now known as Hawking radiation. This process causes the black hole to lose mass, and over eons, it can completely evaporate, disappearing from the universe in a final, faint pop of energy. And here lies the paradox. That final burst of radiation is purely thermal, a random hum of heat. It contains no information about what fell in. All the unique data that made up the stars, planets, or books that crossed the horizon, the very information that light once carried, seems to have been erased from existence. This violates a sacred principle of quantum mechanics, a rule as fundamental as the speed of light itself. Information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. If you burn a book, the information in its words is not truly gone. A hypothetical, infinitely powerful being could analyze the smoke, the ash, and the heat radiation to perfectly reconstruct every single letter. But a black hole, according to Hawking's original math, performs the ultimate act of cosmic arson, burning the book and leaving behind only featureless ash. Resolving this paradox has become a central quest in physics, forcing theorists to propose breathtaking new ideas about the nature of reality. The holographic principle suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic DVD storing a three-dimensional movie. The surface of the black hole becomes a vast, pixelated screen, holding a perfect description of everything within. String theory and loop quantum gravity offer other potential solutions, painting a picture where the event horizon is a seething, complex structure, or where information slowly leaks out in the Hawking radiation after all, encoded in subtle correlations between particles. This is not just an abstract debate. The fate of information inside a black hole is a direct test of our search for a theory of quantum gravity, a framework that would finally unite the large-scale rules of Einstein with the probabilistic weirdness of the quantum world. It asks the most fundamental question of all: when light, the universe's most reliable messenger, is finally and utterly trapped, what story does it tell? On August 15, 1977, a routine sky survey at the Big Ear radio telescope in Ohio printed out a string of letters and numbers. An astronomer named Jerry Amon, reviewing the data days later, saw a column of code so extraordinary he circled it in red pen and wrote a single, powerful word in the margin. Wow, that column represented a radio signal, a burst of energy that was both incredibly powerful and bizarrely pure. It was a narrowband signal focused on one specific frequency, just what you would expect from an engineered transmitter rather than a chaotic natural event. It lasted for 72 seconds, the exact duration the Big Ear could hold a fixed point in the sky, rising to a brilliant peak and then fading away. In that single minute, it screamed its presence from a region of space in the constellation Sagittarius, a potential hello from the cosmos. Yet when astronomers pointed every instrument they could back at that patch of sky, they heard nothing. No repeat, no echo, not even a whisper. It was a one-time event, a cosmic shout that fell silent as suddenly as it began. The search for an explanation has spanned decades. Could it have been a reflection from a human satellite or a piece of space debris? The signal's characteristics make that incredibly unlikely. Was it a completely new type of natural astrophysical phenomenon, a quirk of the universe we have not yet classified? No known cosmic event, from a pulsar to a comet, fits the unique profile of the WOW signal. This leaves one tantalizing, humbling possibility. It might have been a message. A lighthouse beam from a distant civilization, sweeping across our solar system for just 72 seconds, a fleeting moment when our primitive antenna was pointed in precisely the right direction to catch its passing glow. The WOW signal embodies the entire spirit of the search for extraterrestrial intelligence. It is the ultimate tease, a data point of profound promise and absolute frustration. It offers no proof, only a haunting question. For one brief minute, we may have heard another voice using light, or in this case its radio cousin, as a messenger. It reminds us that our listening post on this pale blue dot is still very new, and the cosmos is vast and full of whispers we are only just learning to hear. In a quiet corner of a Cambridge radio observatory, a graduate student named Jocelyn Bell detected a signal that defied all explanation. It was a series of sharp, perfectly regular pulses, arriving every 1.337 seconds with a precision that seemed almost artificial. For a brief, thrilling moment, the team half-jokingly labeled the source LGM for Little Green Men, wondering if they had stumbled upon a beacon from an advanced civilization. The truth was far more extraordinary. They had discovered the first pulsar, a cosmic lighthouse born from stellar death. A pulsar is the collapsed core of a massive star that went supernova, a neutron star. Squeezing more than the mass of our Sun into a sphere just a dozen miles across, A single teaspoon of its material would weigh billions of tons. This incredible density gives it a ferocious gravitational pull and a magnetic field trillions of times stronger than Earth. As it rotates at dizzying speeds, sometimes hundreds of times per second, it shoots out powerful beams of radiation from its magnetic poles. If these beams are misaligned with the star's rotation axis, they sweep across the cosmos like the spinning light of a lighthouse. From our vantage point, each sweep appears as a flash, a pulse of radio waves, X-rays, or even visible light. The metronomic regularity of these pulses is what makes pulsars truly phenomenal. Their timing can be more precise than the most advanced atomic clocks built by humans, their rhythm unwavering over decades. This incredible precision turned them into the universe's ultimate natural laboratories. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pair of pulsars orbiting each other, a binary system. By meticulously tracking the subtle changes in their pulses, they could measure how the stars' orbits were slowly decaying. The stars were losing energy in exactly the way and amount predicted by Einstein's theory of general relativity. They were radiating energy away in the form of gravitational waves, providing the first indirect but stunningly precise evidence that these ripples in spacetime were real. This discovery, which later earned a Nobel Prize, showed that we could use the steady blink of these distant clocks to probe the very fabric of the cosmos. Their potential stretches even into the realm of future exploration. Imagine a spacecraft venturing into the interstellar void. Without familiar stars to guide it, how would it navigate? Scientists have proposed using pulsars as a galactic positioning system. Each pulsar has a unique signature, its own specific rhythm and location. By comparing the arrival times of pulses from multiple known pulsars, a ship could triangulate its position anywhere in the galaxy with phenomenal accuracy. These lighthouses would guide our journeys between the stars, from testing the limits of gravity to mapping the galaxy. The humble pulse of a neutron star is a profound message. It tells us about the behavior of matter crushed to its absolute limit, about magnetic fields of unimaginable power, and about the subtle geometry of spacetime itself, all broadcast in a rhythm more reliable than any human invention. A single gamma-ray burst can briefly outshine every star in its entire host galaxy. These are the universe's most powerful explosions, colossal detonations that flood the cosmos with high-energy light. For a few fleeting seconds, or sometimes just milliseconds, a GRB unleashes more energy than our Sun will produce across its entire 10 billion-year lifespan. The source of such unimaginable violence is the death of a massive star or the cataclysmic merger of two neutron stars. In both cases, the result is often the same, the birth of a new black hole. This is not a gentle creation. It is a chaotic, furious event where matter is torn apart and accelerated to near light speed, focused into twin jets that blast outward like cosmic blowtorches. The gamma rays we detect are the direct signal from these jets, a final, brilliant scream announcing a fundamental change in the architecture of the universe. When one of these jets happens to be pointed directly at Earth, our satellites record a sudden, intense flash from the depths of space. The light from these events has often been traveling for billions of years, a messenger from an era when the universe was young. It carries an encoded story of extreme gravity, relativistic matter, and stellar collapse. But the main burst of gamma rays is only the opening act. As the jets slam into the surrounding interstellar gas, they create a lingering afterglow that radiates across the entire electromagnetic spectrum, from X-rays to radio waves. This is where the real detective work begins. The moment a satellite detects a burst, it automatically sends out an alert to observatories around the world and in orbit. A global race against time commences. Telescopes swivel, desperately trying to pinpoint the fading afterglow before it vanishes forever. Catching that afterglow is everything. Its color and rate of fading tell astronomers the distance to the burst and the nature of the explosion that caused it. Each observation is a precious piece of a puzzle, a fragment of a story about the most violent events since the Big Bang itself. These brilliant, fleeting fireworks are the ultimate test of our readiness to listen, challenging us to decode their message before the cosmic curtain falls. That faint cosmic hiss of static picked up by Arno Penzias and Robert Wilson was far more than a technical nuisance. It was the echo of creation itself, the cosmic microwave background. This is the oldest light we can ever see, a fossilized glow from a time when the universe was a mere 380,000 years old. Before this moment, the cosmos was a searing, opaque fog of plasma, too hot for light to travel freely. Photons were trapped, constantly bouncing off a dense soup of electrons and protons. But as the universe expanded and cooled, a monumental transition occurred. Electrons and protons finally combined to form the first atoms, a process we call recombination. Suddenly, the fog cleared. The photons, once trapped, were set free on a journey across the cosmos. The light that began its voyage that day has been stretched and cooled by the expanding universe for over 13 billion years, arriving at our telescopes as a faint microwave whisper, just a few degrees above absolute zero. This ancient afterglow is not perfectly uniform. Exquisite maps from satellites like Planck reveal a mottled sky, a tapestry of tiny temperature variations. These minute-hot and cold spots, fluctuations of just a few millionths of a degree, are the universe's most important imprint. They are the gravitational seeds from which everything we see eventually grew. Slightly denser regions, revealed by slightly warmer spots in the background, held just enough extra gravitational pull to attract more matter over eons, eventually collapsing into the vast cosmic web of galaxies, clusters, and superclusters we observe today. The precise pattern of these fluctuations acts as a cosmic ruler. By measuring their size and distribution, cosmologists can take the universe's vital signs. This primordial light tells us the exact age of the cosmos, its overall geometry, and its composition down to a fraction of a percent. It confirms the overwhelming presence of dark matter and dark energy, and provides our strongest evidence for a breathtaking event called inflation, a moment of hyper-expansion in the very first fraction of a second after the Big Bang. Decoding this light is truly like reading the universe's birth certificate, a detailed record of its origins, its ingredients, and its ultimate fate. Our cosmic listening posts are growing ears of unimaginable sensitivity. The race to decode light's faintest signals has pushed us beyond the limits of traditional cameras like the CCD. We are now entering the age of the quantum sensor, where we do not just capture light, we interrogate each individual photon. Imagine a detector so precise it can count single particles of light and timestamp their arrival with a precision of a trillionth of a second. This is the power of a superconducting nanowire single photon detector. At temperatures colder than the void between galaxies, a tiny wire becomes so sensitive that a single photon striking it breaks its superconductive state, creating a measurable electrical pulse. It is like having a microphone so fine it can hear the rustle of a single leaf in a silent forest. Alongside these, quantum-limited amplifiers now allow us to listen to light's quietest murmurs without adding the familiar hiss of classical noise that has always obscured the faintest cosmic signals. Why does this matter? For the search for Earth-like exoplanets, it means we might finally detect the minuscule dimming of a star as a tiny, rocky world passes in front of it, an event lost in the noise for older instruments. For fundamental physics, it allows us to test the very foundations of quantum mechanics by observing how single photons behave in bizarre, entangled states. And the future holds even more radical possibilities. Future observatories might use the spooky connection of quantum entanglement itself to achieve a resolution far beyond what classical physics allows. By linking photons across vast distances, we could effectively create a quantum telescope, an instrument with a virtual lens as wide as the separation between its components, seeing details on distant worlds we once thought were forever out of reach. These are not incremental upgrades, they are a fundamental shift in our relationship with the cosmos. We are building ultra-sensitive ears to listen to the universe's quietest conversations, ensuring that every last whisper carried on the stream of photons from the depths of space will eventually be heard. The sheer volume of data pouring from our cosmic observatories is almost beyond human comprehension, a flood of light that would drown any single mind. We are not just collecting images anymore, we are amassing petabytes of information, a digital universe of light curves, spectra, and pixelated whispers. To find meaning in this ocean of data, we have forged a new kind of partnership, one that pairs human intuition with the tireless pattern recognition of artificial intelligence. These machine learning algorithms are the ultimate assistants in our cosmic detective agency. They can sift through millions of star fields in the time it takes to blink, flagging the subtle, telltale signs of a distant exoplanet crossing the face of its star. They scan for the faint, stretched arcs of light that betray the presence of gravitational lenses, where the mass of a foreground galaxy bends the light from one far behind it, creating a natural telescope. They can even classify the shapes of billions of galaxies, sorting elegant spirals from fuzzy ellipticals, a task so vast it would take a human a lifetime. This is not about replacing the astronomer. It is about amplifying their vision. Artificial intelligence handles the initial, monumental chore of filtering the signal from the noise, presenting the most promising candidates for a human brain to then interpret, to ask the next question, to feel the spark of curiosity. This synergy is already revealing celestial objects and events that do not fit any known pattern, strange outliers in the data that might be the first hint of an entirely new class of phenomenon. It is a collaboration that is fundamentally accelerating our ability to listen, ensuring that no precious message carried across the light years is ever lost in the static. A single cosmic cataclysm can now be witnessed with all of our senses at once. We are no longer just watching the universe, we are listening to its vibrations and feeling its faintest ghostly touches in a revolutionary new field called multi-messenger astronomy. The power of this approach was spectacularly proven in August 2017. Gravitational wave observatories, LIGO and Virgo, felt a distinct ripple in spacetime, the signature of two incredibly dense objects spiraling together. Just 2 seconds later, space-based gamma-ray telescopes saw a brilliant flash from the same patch of sky. An alert went out to observatories across the globe and in orbit. What followed was an unprecedented scientific scramble. Telescopes of every kind swiveled to watch, capturing the event in visible light, X-rays, and radio waves. They had pinpointed the source, a neutron star merger in a galaxy 130 million light-years away. For the first time, we could correlate the gravitational wave chirp with the brilliant optical glow of newly forged heavy elements like gold and platinum, literally seeing the universe create precious metals in a violent cosmic forge. This was not just one observation, it was a chorus. Each messenger brought a unique part of the story. The gravitational waves told us about the masses of the objects and the dynamics of their final dance. The neutrinos, though not definitively detected this time, would have carried news directly from the heart of the collision. the light across the spectrum showed us the aftermath, the expanding debris, and the radioactive decay of new elements. It is the difference between hearing an explosion from another room and then walking in to see the smoke, feel the heat, and analyze the shrapnel. Only together do they reveal the full truth. This synergistic approach is fundamentally reshaping astrophysics. It allows us to cross-check Einstein's theories under extreme conditions, to understand the origin of the heaviest elements, and to measure the expansion rate of the universe in a completely new way. We are moving from studying isolated snapshots to witnessing entire cosmic narratives unfold in real time, using every tool at our disposal to read the universe's grandest stories. Our universe runs on delayed information. The very act of seeing is an act of time travel into a past that has long since vanished. When you look at the stars, you are not seeing them as they are tonight, but as they were centuries, millennia, even millions of years ago. The light from our own sun is a snapshot from over 8 minutes in the past. If it were to suddenly blink out, we would not know for those 8 agonizing minutes, living in a phantom reality built on old news. This fossil light surrounds us, a cosmic museum where every glance upward is a look into a history book written in photons. This simple fact dismantles the idea of a single, universal present moment. Einstein's Relativity of Simultaneity, a direct consequence of light's fixed speed, proves that 2 events occurring at the same time for one observer can happen at different times for another moving observer. There is no master clock for the cosmos, no universal now that ticks for everyone and everything. Your present and the present of a being in a distant galaxy are not the same. Time itself is a local, personal experience, stitched together from signals that arrive at different moments. Then we descend into the quantum realm, where entangled particles whisper to each other across any distance with what seems like instant connection. This non-locality suggests that the fabric of reality is woven with threads that ignore our conventional notions of space and separation. The universe appears to be deeply interconnected in ways that defy the very speed limit it enforces for everything else. So what is real? Our perception of a solid, objective world is a carefully constructed illusion, a story our brain compiles from sensory data that is always, inevitably, out of date. We are not passive observers of a fixed reality. We are active participants assembling a coherent present from a chaotic flood of messages, each one stamped with a different time and place of origin. Physics and metaphysics begin to merge into a single, profound inquiry. The ultimate message from our fastest cosmic messenger might be the most humbling of all, that reality is not a static stage we stand upon, but a dynamic, relational tapestry we are forever weaving from the light of the past. Those same principles that govern light across the cosmos are now woven into the fabric of our daily lives. Our relentless quest to understand the universe's fastest messenger has spawned technologies that feel like pure magic, yet they are direct applications of those fundamental cosmic laws. Consider the simple act of checking your location on a phone. The Global Positioning System is a network of satellites, each carrying an incredibly precise atomic clock. But these clocks are moving fast relative to the Earth's surface, and they are also higher up in our planet's gravitational well. According to Einstein's theories, this means they experience time differently. Special relativity says their speed makes their clocks tick slower, while general relativity, accounting for the weaker gravity, says they tick faster. The gravitational effect actually wins out. If engineers did not deliberately program the satellite clocks to run slightly slow before launch, compensating for these effects, the entire system would drift into uselessness within mere minutes. Your map would be wrong by several miles after just one day, so every time you use a GPS, you are relying on a direct, engineered correction for the warping of spacetime itself. Then there is the laser, a device that feels almost science-fictional. It is a product of our quantum understanding of light, forcing photons to march in a perfectly orderly, coherent beam. This single invention now touches nearly every part of modern existence. It reads the data from DVDs and Blu-ray discs, scans your groceries at the supermarket, and guides the precise cuts of surgeons repairing a retina or removing a tumor. It forms the backbone of the global internet, carrying countless conversations and cat videos as pulses of light through hair-thin glass fibers. In the medical realm, the legacy of decoding light is just as profound. Magnetic resonance imaging, or MRI, uses powerful magnetic fields and radio waves, a form of light, to peer non-invasively into the human body. It manipulates the spin of atomic nuclei in your cells, listening for the faint radio signals they emit as they relax, building a detailed map of our soft tissues. A positron emission tomography, or PET scan, tracks a radioactive tracer injected into the body, detecting the gamma rays produced when positrons and electrons annihilate each other. This is not just medical technology, it is applied particle physics. These are not happy accidents. They are the dividends of a deep and abiding curiosity, proving that the race to answer the most profound questions about the cosmos so often hands us the tools to transform our own world. The cosmos should be teeming with voices. With countless stars and billions of potentially habitable worlds, the galaxy ought to echo with the radio chatter and laser light of other civilizations. Yet when we listen, we hear only a profound and unsettling quiet. This is the heart of the Fermi Paradox, a question that has haunted our search for cosmic company. If life is common, where is everybody? For decades, our primary method of listening has been to scan the skies for radio waves, the same kind of electromagnetic signals we have been broadcasting for over a century. We have also searched for powerful, deliberate laser pulses, flashes designed to catch our attention across the interstellar void. The result, so far, is a resounding silence. This great quiet is not for a lack of trying. Projects like SETI have tirelessly monitored the heavens, sifting through cosmic static for any pattern, any rhythm, any signal that screams of artificial origin. The continued absence of such a signal is a puzzle with many potential solutions, each one a story about the nature of life and intelligence. Perhaps technological civilizations are incredibly rare, arising only under a perfect and fleeting confluence of conditions. Maybe they are common, but they are tragically short-lived, destroying themselves with war, environmental collapse, or technologies they could not control long before they master interstellar communication. Another possibility is that we are simply listening on the wrong channels. Our technology is primitive, built around the narrow slice of the electromagnetic spectrum we find useful. A more advanced civilization might have long ago moved beyond radio and light, using the ghostly streams of neutrinos or the subtle ripples of gravitational waves to send their messages. We are only just learning to detect these cosmic messengers ourselves, so their conversations would be entirely invisible to our current instruments. Or perhaps the answer is simpler and rooted in the very nature of light speed itself. The universe is vast not just in space but in time. A civilization in a galaxy 100 million light-years away could have flourished and fallen while dinosaurs still roamed our planet. Their final, desperate broadcasts, their greatest works of art and science, could be streaming through space right now, a flood of information traveling at the ultimate speed limit. But that light has not reached us yet. We are living in a cosmic bubble of silence, waiting for news that is already on its way but has not arrived. This great silence is itself a form of message. It forces a humbling contemplation of our own place in the cosmos. Are we a fleeting, lonely spark in a dark and empty universe? Or are we simply one voice among many, waiting for our time to join a conversation that has been going on for eons, a conversation whose first words are still traveling toward us at the speed of light? Our cosmic view is framed by an ultimate boundary, a horizon beyond which no light can ever reach us. This is not a wall of rock or a curtain of dust, but a consequence of the universe's own relentless expansion. Think of space itself as a vast, stretching fabric with galaxies stitched into its weave. For the most distant galaxies, the space between us is growing so rapidly that the light they emit, traveling at its maximum cosmic speed, is fighting a losing battle against the stretching void. The photon is like a swimmer in a current that flows faster than they can swim, forever receding from the shore of our telescopes. This boundary is known as the cosmic particle horizon, and it defines the absolute limit of our observable universe. Everything we can possibly see, from the nearest star to the most distant quasar, exists within this bubble, but the universe almost certainly does not end at this horizon. It stretches on, perhaps infinitely, into realms whose light will never have time to reach us before the expansion of space carries them away forever. This raises a deeply unsettling question. What lies in those unobservable regions? Are the laws of physics the same there? Is the cosmos filled with more galaxies, stars, and planets? Or could there be entirely different structures, forms of matter, or even variations in the fundamental constants that govern reality? We simply have no way of knowing. The light from those regions is not just delayed, it is permanently lost to us, its message eternally redshifted into nothingness. This horizon is a humbling reminder of our own isolation within the cosmos. We are not at the center of the universe, but we are at the center of everything we can ever know. Our entire understanding of reality is built upon the finite collection of photons that have managed to cross this unimaginable gulf. The ultimate mysteries may not be in the distant past or the far future, but in the vast, invisible now that surrounds us, forever just beyond the reach of our fastest messenger. A distant star flickers, and in that almost imperceptible dimming, an entire world is revealed. The hunt for exoplanets is a masterclass in reading the subtle language of light, transforming a star's steady glow into a storybook of hidden planets. The most prolific technique is the transit method. Imagine a firefly passing in front of a distant searchlight. From our vantage point, the light dips by a tiny, almost unmeasurable fraction. That is what our telescopes detect when an alien world crosses the face of its star. This momentary eclipse, this faint shadow, tells us the planet's size and the length of its year. But the star itself also moves, pulled by the gentle gravitational tug of its orbiting worlds. This is the radial velocity method. As the star is tugged toward us and then away, its light is compressed and stretched, creating a tiny Doppler shift in its spectrum. By measuring this stellar wobble, we can calculate the planet's mass, a small, rhythmic dance between star and planet, written in the shifting colors of starlight. For a handful of systems, we can attempt the most difficult feat of all, direct imaging. Using advanced coronagraphs to block the star's blinding glare, like shielding your eyes from a street lamp to see a moth circling nearby, we can sometimes capture the faint, reflected light of the planet itself, a pale dot of cosmic companionship. Yet the most profound insights come from a transit. As the planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Molecules in that alien air absorb specific wavelengths of light, leaving their unique fingerprints on the spectrum. By decoding this filtered starlight, we can read the atmosphere's chemical composition from light years away. We search for the telltale signs of biological activity, for biosignatures like the persistent presence of oxygen, which reacts quickly with other elements, or the unexpected abundance of methane. Finding these molecules together would be a powerful, though not definitive, hint that we are not alone. We are using light as a universal diagnostic tool, analyzing the air of distant worlds to answer humanity's oldest question: are we the only life in this vast cosmic ocean? Light speed carves the boundaries of reality itself. It dictates which events can touch one another, ensuring a universe where causes always come before their effects. This rule is woven into the very geometry of spacetime through a powerful concept called the light cone. Picture a single event, a flash of light at a specific moment and place. Now trace all the possible paths that light from that flash could take through time. The result is a double cone shape extending from the past into the future. The region inside your future light cone contains every event you can possibly influence, every place a signal traveling at or below light speed could reach. The region inside your past light cone holds every event that could have ever influenced you. But here is the crucial part: everything outside these cones is forever separate from you. Those events are in your absolute elsewhere. No message, no force, no influence of any kind can bridge that gap, because doing so would require traveling faster than light. This structure prevents paradoxes from unraveling the cosmos. It stops you from receiving a message before it is sent, or from altering an event that has already causally disconnected from you. This means your now and my now are not the same. Your personal present is a unique slice of the universe, defined by the light that has just reached you. For someone on a planet orbiting a distant star, their present moment includes events that are still in your future, and vice versa. There is no universal clock ticking for everyone. The cosmic speed limit enforces a profound and personal reality for every point in space, making causality the most fundamental rule in the book of physics. The speed of light is not just a number we measured. It is a fundamental thread woven into the cosmic tapestry, and its precise value raises a profound question. Why is it this specific number and not another? Some scientists explore a controversial but captivating idea known as the Anthropic Principle. It suggests the universe's fundamental constants, including the speed of light, appear to be perfectly tuned for the emergence of life and conscious observers like us. Think of the cosmic consequences if the speed of light were even slightly faster or slower. If it were much faster, the energy-binding atomic nuclei might not be sufficient, preventing the formation of stable atoms. The universe would be a sea of loose particles with no chemistry and no stars. If it were significantly slower, the universe might have collapsed back on itself long before planets could form, or nuclear fusion in stellar cores might never have ignited. The delicate balance that allows for carbon, for water, for the long-lived stable stars that provide energy and the heavy elements for planets, all of it depends on a very specific set of physical rules. The fact that we are here to point our telescopes at the sky and measure this constant might be the most important data point of all. Our very existence could be a consequence of living in a rare, hospitable pocket of reality where the numbers align just right. This idea places us into the cosmic story in a startlingly active way. We are not just passive decoders of the universe's messages. Our ability to see, to measure, and to wonder is itself a product of the very laws we are trying to understand. The universe may be built in such a way that it eventually grows eyes to look back at itself. Our cosmic ears are about to grow exponentially more sensitive. A new generation of instruments is poised to launch, each a specialized hunter designed to capture a different whisper from the dark. The Nancy Grace Roman Space Telescope will wield a field of view 100 times larger than Hubble's. conducting vast cosmic surveys to map the influence of dark energy with unprecedented detail, and discovering thousands of new exoplanets through its keen gravitational vision. Meanwhile, in the quiet of space, the LISA mission will unfold a triangular constellation of satellites, millions of kilometers apart. This colossal interferometer will listen for the low-frequency rumble of spacetime, the mergers of supermassive black holes that have been silent to our current ground-based detectors. It will tune into the grand, slow-motion collisions that shape the hearts of galaxies. Back on Earth, the Cherenkov telescope array will cover a mountainside with hundreds of dishes, staring into the sky not to see light, but to see the ghostly blue flashes created when ultra-high-energy gamma rays smash into our atmosphere. This will open a window into the most violent particle accelerators in the universe. And then there are the giants rising from the ground, the extremely large telescope and the giant Magellan telescope, with mirrors spanning the width of tennis courts, will use their immense light-gathering power to achieve the seemingly impossible. They will attempt to directly image Earth like exoplanets, analyzing their atmospheres for signs of habitability, perhaps even life. These are not just new telescopes. They are a fundamental expansion of our perception, a collective effort to catch the universe's faintest, most distant, and most subtle messages. They are the physical manifestation of a species that refuses to stop listening, building ever grander instruments to ensure the next chapter in the Chronicle of Light is the most revealing one yet. Our journey through the Chronicles of Light Speed is a testament to an unbroken chain of human wonder. It stretches from the first philosophical questions whispered under ancient skies to the quantum sensors listening in laboratories today. We have seen that light is far more than simple illumination. It is the universe's ultimate data stream, a relentless flood of information carrying the history of stars, the birth of galaxies, and the very structure of spacetime. That single constant, c, is not just a speed limit. It is a fundamental rule woven into the cosmos, dictating the flow of cause and effect and defining what is real for every observer. This race to decode our fastest messenger has utterly reshaped our reality. It has redefined the atom and the expanse of the cosmos, gifting us with profound mysteries like dark energy, while simultaneously delivering the technologies that power our modern world, from global positioning to the internet. We stand on the shoulders of every curious mind who dared to ask how and why, from Rømer's celestial clock to Maxwell's elegant math and Einstein's revolutionary postulates. Their legacy is not a finished book but an invitation to keep reading. The universe has not fallen silent. It is speaking in gravitational waves, in ghostly neutrinos, and in the faint, stretched light of the first galaxies. Our task is to continue building ever more sensitive ears and ever more perceptive eyes, to cultivate not just the tools but the wisdom to understand what we hear. Which cosmic messenger captures your imagination the most? Share your thoughts in the comments and subscribe to join us as we continue this grand journey of discovery.